So in this video, we are going to discuss looking at molecules and figuring out how many equivalent hydrogens there are. So let's take a look at this example right here. And we have CH2. No, let's draw it like how I had it in the problem here. And I did CH2 like that. That's how the molecule is drawn. Now, in order to figure out the equivalencies of these hydrogens, we have to understand that this is not how the molecule looks, right? You cannot view the molecule like this. And why not? Well, what is the hybridization state of that carbon? It's sp3 hybridized, which then tells us that the geometry around that carbon is tetrahedral. So when you see a molecule that's drawn out really plainly like this and doesn't show you the stereochemistry, you have to go in and do that. So if we draw this just as a zigzag structure, let's do it with just a zigzag structure, shall we? Like this. All right. So that's going to be a whole lot easier to draw. So we go from here to here, double checking carbon count. 1, 2, 3, 4, 1, 2, 3, 4. Now we are going to have hydrogens here that are wedges and dashes, like this. And then we can draw in our hydrogen there. Now, we can ask questions like, okay, what's the relationship between this proton and that proton? And you will see that if you do a replacement test, put an X on this, replace an X here, draw the molecule, and then draw a second molecule with an X replacing this hydrogen, you will see that those are constitutional isomers of one another, because you're going to have the same molecular formula, but different connectivity. The X is attached to a carbon on the one molecule, and on the other molecule, this X would be attached to a oxygen. It's just different connectivity, constitutional isomers. So what we can say is that this proton will give us a signal, and I'll call it A. This proton here will give us a signal, and I'll call it B. So we know HA and HB are not equivalent because they're constitutional isomers. Now we have 4 hydrogens that we have to discuss, and doing the replacement test takes a long time to do that. And so symmetry arguments is very efficient in helping us do that. So what we first look at, I pick a axis of rotation, and if I can rotate the molecule 180 degrees, does the two versions look the same or not? If they don't look the same, then there's no axis of rotation. So let's ask the question, what's the relationship between this proton here and that proton there? All right. Now, if you do the replacement test, you will see that they are enantiomers of one another. But I want to show you just using a plane of symmetry argument. So what you're going to do is, these are the two hydrogens in question. What are their relationships with one another? If you take this molecule that's in the plane of the glass and rotate it 90 degrees, and then you just look straight down it, you're going to see the 4 hydrogens on each side, and then the alkyne is just right here. And so I want to hopefully make this work by using a model. So I've never done this before, so let's see if this works. So here's a model of that molecule here. Okay. And so what you're going to do is you're going to take the molecule, like I said, and you're going to rotate it 90 degrees, like this. Okay. Now when you rotate it 90 degrees, we want to get the two hydrogens in question. So this hydrogen and this hydrogen, which is that one and that one. What is their relationship? If I can take it and find a plane of symmetry, that each half of the plane is identical, then those hydrogens are going to be enantiotopic. So watch what I can do here. If I rotate it this way, now look at this bond right here. Watch what I can do. I can rotate it like so. Now get it all lined up there. Do you see how that if I slice the molecule right down the middle right here, I have a plane of symmetry? This side of the molecule and this side of the molecule are identical. This hydrogen, carbon, 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 oxygen atom is split right down the middle. So those 1, 2, 3, 4, 5, 6, and this hydrogen, sorry, 7, these 7 atoms right here in the line, right there, those are cut in half. And so on this side, we have half of the atoms, and on this side, we have the other half. But when you look at it, every half right down this plane is identical. And when you have hydrogens in question, these two, you don't want those chopped in half. You want to find a plane that puts the whole atom on one side of the plane, as shown with this one, and the hydrogen on the other. And so what's cool is that all I have to do in mind's eye or with models, look at this molecule and realize that I could take it and rotate it 90 degrees, and then sometimes you're going to have to rotate bonds. But do you see that plane of symmetry right down the middle? And so that means these two hydrogens right here are going to be enantiotopic. So we can say that those two hydrogens are the same. But are these two hydrogens the same as A? Of course not. Different connectivity. Are these C hydrogens the same as B? Of course not. Different connectivity. Okay? Now, what about these protons? I'm asking the question, are these two, what's their relationship? When we look at the model, there they are. And we do the same trick. There's a plane of symmetry, making those guys enantiotopic. So we'll just go D and D. But we need to double check something. Is C and D, are those equivalent? Are they going to be the same? And so what you can do is you could try to find a plane of symmetry that compares those two. So for example, if I take this molecule here, okay, and I'm asking, what's the relationship between these two protons right here? What's their relationship? So that's what the molecule looked like originally. Now I'm asking, what's the relationship between this hydrogen and this hydrogen? So I need to rotate the molecule in such a way as to get a plane of symmetry. Now there's a plane here. Well, that's not, if I imagine there's a plane here, there's a reflection of the two hydrogens. That's good. But look, I have this alkyne on one side and a hydrogen on the other. So is there a plane of symmetry? No, there's not. Could I go like this? That's bad because now I'm chopping the two atoms of interest or in question. I'm chopping those in half, so I can't draw that plane. So I'm trying to just look and try to see if there's any plane, and there's not. And since there's no plane of symmetry amongst these two hydrogens, they're diastereotopic. And so that would mean, yes, there's C's and D's. So there's going to be 4 signals for this molecule. Okay. Now, obviously, you can do the replacement test. That's if the planes of symmetry doesn't work for you, do the replacement test. So let's do the replacement test for just one of these hydrogens and let's see their relationship, okay? So what if I want to compare this wedged hydrogen and that wedged hydrogen to see what is their relationship? Well, we do the replacement test, take one of them and replace it with an X, and then draw the molecule again. So we place that back like that, okay? So now we'll call this molecule number 1 and this molecule number 2. What's the relationship between these two? Can I take this molecule and superimpose it on number 1? No, I cannot. Is molecule 2 and molecule 1 a mirror image of one another? No, there's not. You can try to find one. So how I'm going to do that is I'm going to flip this molecule 180 degrees so I can get the oxygen atoms to mirror one another. And so when I do that, I'll go like this. And there's the H, there's the wedge, dash, wedge, and a dash. So this carbon has an X on the wedge. So now the X is right there, and that hydrogen has become the wedge. And then these two we don't need to worry too much about. Now what we can see here is when you look at molecule 1, this molecule is still number 2, but we're going to call it 2' because I took this molecule, just rotated it 180 degrees. And so ignoring the X's, okay, do you see how it looks like a mirror image? The oxygen, the carbon, everything aligns up. It's a mirror image when you ignore the X's. But when you don't ignore, wait, let's see. I take that back. They're not mirror images of one another. Okay, let me backtrack here. Yes, ignoring the X's, it looks like a mirror image. But what's going on here? Okay. That X is attached to a carbon with an OH, but this X is attached to a carbon that's not attached to the oxygen. So what's the relationship between these two? Those would be constitutional isomers, right? And not equivalent. So in that particular case, doing the replacement test was rather long, right? But it gets you to the same answer. You can use symmetry arguments, or you can use replacement tests. So let's take a look at this molecule. Like that. How many chemically distinct protons are there? All right, so we have all these protons right here, like that. So we could do a symmetry argument here. And what makes this molecule easy to work with is the fact that all these carbons are sp2 hybridized. So this molecule is completely flat. So it's a whole lot easier to find planes of symmetry now. So if we are asking the question, what's the relationship between this hydrogen and this hydrogen? We have an axis of rotation. Watch this. Watch what we can do here. I'll label that number 1 and that number 2. I have an axis of rotation that if I take it and spin it 180 degrees, are you able to tell the difference between the two versions here, before and after the bond rotation? And I'm not going to draw the other hydrogens, just to keep it simple there. So now, You see how I just took this molecule, flipped it 180 degrees? If you did not have the numbers, would you be able to tell that I rotated this molecule 180 degrees? And you'd be like, no, I can't tell the difference between the two. And so when you have a bond of rotation or axis of rotation, that means these two protons are homotopic and they're equivalent. So that would make this proton and this proton equivalent, so they're both A, meaning these two protons are going to give one signal. If those two are equivalent, then that would make these two equivalent as well. But what's the relationship between HA and HB? Well, they would be constitutional isomers because they have different connectivity. Because you can see HA is bound to a carbon that's right next to a carbon with a chlorine on it. Whereas this carbon hydrogen right here is 1, 2 spaces away from the chlorine. Different chemical environment. And then this proton right here is just all by itself, so we would just call it HC. So in this chlorobenzene right here, we would have 3 signals. Now, what if we changed it up by adding another chlorine here? What if I put a chlorine there? Okay. Now, if I did that, okay, and took this molecule, well, first we have to determine which hydrogens we're looking at. What's the relationship between these two? So I want to do the axis of rotation first. So if I do that, and I take this molecule and rotate it, what is that going to look like over here? Well, we're going to put the chlorine there now, right? Take that molecule, flip it 180 degrees, the chlorine's there. And so this is before the rotation, this is after. Do you see a clear difference? Okay. So they're not homotopic. Okay, not homotopic at all. So are they enantiotopic? With enantiotopic hydrogens, you're trying to find a plane of symmetry. Is there a plane of symmetry that makes each half the exact same? So the 2 protons in question are still these. If I try to draw a plane of symmetry right down the middle here, you can see that this half, well, let's just do it right here. This half looks different than that half. So there's no plane of symmetry there. All right. Now, could we have drawn, let's draw the molecule again over here. Put the chlorine here. Now we have to keep in mind, what 2 protons are we looking at? It's these 2. So could we draw a plane of symmetry here? Just right through there like that? And the answer is yes, we do have a plane of symmetry. This side is identical to that side. This proton split in half, that proton split in half. But you remember what I said when you're comparing 2 protons and you find a plane of symmetry? You cannot cut the atom of interest in half. They have to be whole atoms on either side of the plane that you decide. So that's not the correct plane of symmetry we're looking for. All right. So if you try to find a plane of symmetry like I did with this one to get the 2 hydrogens on either side, you will realize very quickly that you cannot find a plane of symmetry because this chlorine messes it up. So since there's no plane of symmetry between those 2 protons of interest, that's going to make those 2 protons non-equivalent. Okay. Did I cut that off? Barely cut off the chlorine there. So we could call that HA and that's HB. Like that. So what's the relationship between those two? Those would be constitutional isomers of one another because when you do the replacement test, you'll see different connectivity, same molecular formula. Okay, what's the relationship then between HA and this proton right there? And using symmetry arguments, we could figure it out really quickly. If I take this molecule, flip it 180 degrees, would you be able to tell the difference between the two? Let's see here. What if I drew it more like this? Let's see here. So I'm going to put HB right there. So that means the chlorines are right there and there. And we have our hydrogen like that. So that's our HA. So all I've done to this molecule is just rotated it to look like this. And this is just going to help me better understand what's the relationship between this proton and this proton. Do we find an axis of rotation? If I take this molecule and rotate it upon this axis right here, what would we see? HB, and this would be our HA, A, okay. So before rotation, after rotation, if there were absolutely no labels, no A's or B's, would you be able to tell the difference between the two? No, you wouldn't. So that makes this proton right here equivalent to A. In which manner? All right. Well, what if I took this guy? Can it superimpose? Yeah. If we did the replacement test, we would see that they can superimpose on one another. So if we just use symmetry, because there's a bond of rotation around an axis, that makes those guys homotopic. If we want to do the replacement test, then we can do that and see if they're the same. So if we don't want to look at looking at the axis of rotation and just do the replacement test. So what's the relationship between these two? Well, let's do the replacement test. Remove that hydrogen, and then we'll remove this hydrogen and replace it with an X, but over here. All right. What's the relationship between A and B? Well, can I take B as drawn and pick it up and just superimpose it on A? No, I cannot. But I can take B and rotate it 180 degrees, and now the X is right there. And this version is still molecule B, it's just rotated 180 degrees, so I call it B prime. Now can I take B prime, pick it up, and smack it right on top of A? Yes, I can. So what's the relationship between those two? They're identical. And since they're identical, that makes this proton and that proton homotopic. So HA and HA. And then the last one, you can see that HB is sandwiched between two chlorines. This hydrogen is sandwiched between two protons. Different chemical environment. The relation, so that's going to be its own unique chemical signal. So this one also has one signal. So got to be very careful here. How many protons do we have? 1, 2, 3, 4. But how many signals do we have? Only 3. 1, 2, 3. So let's take a look at another benzene. Let's look at a para-substituted benzene. So we have protons there, there, there. Okay. Now, when we start this process of trying to figuring out which hydrogens are equivalent or not, we have to select two groups of hydrogens or two single hydrogens and ask the question, what's their relationship? And there's no right or wrong way to do it. I'm just going to say, what's the relationship between this hydrogen and that hydrogen? And if I do the replacement test, that would look something like this. We'd go X, hydrogen, hydrogen, hydrogen. So that's molecule A. Do it again. We will now replace this hydrogen with an X and ask ourselves, what's the relationship? So that's B. Do you see if I take this molecule, B, and flip it 180 degrees this way, so bringing this chlorine up top, like that, okay, what would we get? So that's chlorine 1. Chlorine 1 is now there. Let's see, that will now be the X, H. We'll call that B prime. Do you see how I can take B prime and pick it up and superimpose it right on top of A? So that makes those two molecules right there identical to one another. So that means this proton and this proton are homotopic and hence equivalent. So if we do the same question, what's the relationship between these two protons? You will see using the replacement test, they are also homotopic. So if this one and this one are homotopic, and this one and this one are homotopic, then they have to give the same signal. So in this particular example, we have 4 protons that give rise to only one signal because all the protons are homotopic. So that's how you would do it with the replacement method. But what about planes of symmetry? Well, if you ask, what's the relationship now between, let's say, this one and that one, do you see how that if you have a axis right here, just right down the middle, if you have an axis and you spun it 180 degrees, you would not be able to distinguish before the rotation and after the rotation. There's a beautiful plane of symmetry right there when comparing this proton and that proton. Axis of rotation going this way, before and after you won't see a difference, so that makes them homotopic. Also, if you're asking the question between those two, this one and that one, now you have an axis of rotation this way. If you take that molecule and rotate it that way, 180 degrees, you would not be able to tell the difference between before or after the rotation. Hence these two protons, because there's a axis of rotation, then those are going to be homotopic as well. Okay. So let's do let's do this benzene derivative. Let's see, what if we had Is that coming up on the screen okay? Looks like. What if we put a chlorine there and an alcohol there? We have an H like that. I don't think those markers are coming in very nice. So what's the relationship then, let's say, between this guy and that guy, H1 and H2? What's the relationship there? Well, is there an axis of rotation right down here? If I flip it 180 degrees, we would clearly see that the OH will now be on top and the chlorine will be on bottom. So you would see a difference. So the relationship then between these two, there's no axis of rotation. Is there a plane of symmetry that cuts them in half? If I go right down here, there's no plane of symmetry because we have an OH there and a chlorine there. So that would have to make those guys right there constitutional isomers or non-equivalent. So we'll call that A and that B. But what's the relationship between this proton and that proton? Is there an axis of rotation? Well, if I have an axis right here, okay, and I take that molecule and flip it 180 degrees this way, would you be able to distinguish before the rotation and after? No, you won't. It's going to be exactly the same molecule. So this guy is homotopic with this guy, hence they're equivalent. And if those two are equivalent to one another and homotopic, then those two would also have to be the same. So these two are homotopic. Those two are homotopic to one another, being equivalent. And then how many signals does this molecule have? We have 1, 2, and then we would have 1 for that hydrogen right there. So we would have 3 signals for that benzene derivative. All right. Okay, so here's a question. So I'm going to draw the 4 versions up here, and then we will read the question. Okay, the question states, a compound gives rise to 2 signals in its proton NMR spectrum. Which of the compounds, D through G, can it be? Explain. Okay, so I'm going to go through this fast, and I'm not going to go into detail as to how I know this, but the short answer is do the replacement test or do axis of rotation or planes of symmetry to figure this out. So we would say, hey, okay, so that's a signal. Okay, those are homotopic to one another, and then we would have HB right there. So that guy gives 2 signals right there. Now this one here, we have HA, HB, and HC. So we have 3 signals for that guy. We have a proton there. So that's A, B, and C. 3 signals on that one. And then this one, we have a proton there, proton there, and a proton there. So let's take a look at this here. We could use symmetry arguments here. No, that's not. That's A, B, and C. So what we have there, 2 signals, 3, 3, and 3. So the question asks, which of the compounds can it be? D is the one that gives us 2 signals. And when the question asks to explain, you would go through each one of them and say, you could talk about planes of symmetry to prove why this has 3 signals. And same with that, plane of symmetry, why does that have 2 signals? Or you could do the replacement test. Well, that's what that question is asking you to do, is to go through that work and effort to explain why you have the signals that you do. Now, something I should have said at the beginning of the video, but I'll say it now, is when I put these problems up here, it would be a good idea that you pause the video and try to answer them before you listen to my answer and see if you come up with the same thing. So let's take a look at this molecule here. How many signals would you expect for this guy? Well, so there's only 2 protons, so we have to determine what's the relationship between those 2. And look at what I see right down here. I can see an axis of rotation. Before and after a rotation around that axis, you won't be able to tell the difference between those 2 protons or between those molecules. So that would make those 2 protons equivalent, and they are homotopic. So there would only be 1 signal in that molecule. If you do the replacement test, you would come up with the same answer. But I want to kind of get away from doing the replacement test and do symmetry arguments to help us figure it out. Now, that's the molecule that's given to you. That's how it's shown. But we're organic chemists, so we know that there's protons on those carbons, and those are tetrahedral, so we have those 2 protons there. So now it begs the question, well, there's lots of questions we have to ask about this one. So we see that this is a methyl, right? So we already know that these 3 protons are equivalent to one another. And there's also a methyl right there. That those 3 are equivalent to that. But the question is, what's the relationship between these 2 methyls? Are they equivalent to one another? And what you can do is, if I took this molecule drawn as is, and I'm asking, are these 2 equivalent? And I draw a plane right down the middle right here, do I have a plane of symmetry? And the answer is yes, because remember, the methyl, or the wedge and the dash, they're sticking out of the glass and into the glass. So these 2 methyls right here, if I draw a plane of symmetry right down the middle, I have an equal half. I have the hydrogens on either side of the plane, and then these methyls right here, they're getting chopped right in half. So if you just pay attention to the carbons, I'm chopping those carbons right in half. But remember, when we draw a plane of symmetry like that, that's not going to work, because I'm asking, are these equivalent or not? So we cannot draw the plane right through those atoms. But if you take this molecule and take it, if my hand represents the triangle, and if you take it and rotate it 90 degrees like this, and then look down it from that way, you will be able to take that triangle and slice it. There's going to be a plane now right down there where the 2 methyl groups are on either side. So maybe I should make a model of this real quick, and hopefully you can see that. Okay, so here's my model, like that. Now these two methyl groups right here, I did not put in the hydrogens on those two carbons right there, just to make it look a little bit more simple. But yes, there are going to be 3 hydrogens on those, okay? So the question is, what's the relationship between those two methyls? And I said if you draw a plane of symmetry right down here, yes, there is a plane of symmetry, but we cannot chop the two methyls in half with that plane. So if you take that molecule and rotate it 90 degrees like that, all right? Now do you see, if I slice it down this way, that there's a plane of symmetry? I have a methyl on each side of the plane. The hydrogens match up. Everything matches up. There's a perfect plane of symmetry. All right? But looking at the axis of rotation first, let's do that. So there is a plane of symmetry, so that makes those equivalent. Okay? But are they enantiotopic or homotopic? Well, I have a plane of symmetry, so you might say enantiotopic, but you have to be careful because is there an axis of rotation? Watch this. If I take this and rotate it 180 degrees, do you see a difference between that orientation and that orientation? You could not tell the difference. So because of that axis of rotation, that makes those methyls homotopic. They're equivalent. So on exams, if you saw that there's a plane of symmetry, you'd be like, yes, they're equivalent. Great. You got half of the question right. Because the follow-up question would be, well, are they homotopic or enantiotopic? And if you got to see if there's an axis of rotation. So homotopic, okay? Now, what's the relationship between these two protons? Well, we have a plane of symmetry. Straight down the middle. Now I can chop the methyl groups in half because now the atoms in question are this guy and this guy. So I chop it right in half and there's an equal plane of symmetry. So that makes those two equivalent. All right? Are they homotopic or enantiotopic? Those are the two protons. And if I did an axis of rotation 180 degrees, could you tell the difference before and after? No, you cannot. So now we have to ask the question, what's the relationship between those two? Well, if the two wedged ones are homotopic, then those would have to be homotopic as well. So we could go C, C. But now we need a pause just for a second. Well, what's the relationship between C and B? All right, so let's hold up our model here. So C and B, or B and C, it doesn't matter which, okay? And we take a look at that. All right. Can we see a plane of symmetry right down the middle right there? So what's the relationship between those two? There's a plane of symmetry. So that makes them equivalent. All right. So if they're equivalent, if this and this guy are equivalent, then they have to be B. Okay. And if we're comparing these two hydrogens on the same carbon, shown right here, is an axis of rotation. Before rotation, after rotation. Did you see a difference? No, you didn't. So those are homotopic as well. So they're all homotopic right there. So what we would see in NMR is we would have one signal for A and one signal for B. So there's a lot of protons, but only two signals. Okay. So what if we change this up a little bit now? Okay. How many signals would you expect from this guy? Okay. So now we have our methyls here. Got to make sure we understand those are methyls. And then a good thing to be aware of, hey, there's some protons here. And then that's a sp3 hybridized carbon, which means it's tetrahedral. So we have hydrogens like that. So lots of protons here. We got to figure out what are we going to ask? The thing that jumps out to me right now are those methyl groups right there. What's their relationship right there? Well, I see that there is a plane of symmetry cutting right down that triangle, and there's an equal half on each side. So that makes those two equivalent to one another because there is a plane of symmetry. So those are equivalent to one another, but are they homotopic or enantiotopic? Well, if we take our model kit and change it up a little bit, okay. All right. Just see that there? So now our methyls right here are sticking out at you. So I see a plane of symmetry right here, so that makes those equivalent. But are they homotopic or enantiotopic? Well, let's look at it. Before rotation, after rotation. Do you see a difference between the two? Yes, you do. So there's no axis of rotation right here. All right, none. Because you can clearly see a difference before rotation and after rotation. So those two are enantiotopic to one another. If those are enantiotopic to one another, then those would also have to be enantiotopic to one another, right? Okay, now what about the relationships between this proton and that proton? Well, they're different connectivity. They're on different atoms. This hydrogen is attached to a carbon that's attached to a methyl. This hydrogen is attached to a carbon attached to two other carbons. See, they're just different connectivity. If you do a quick replacement test, you'll be like, hey, those are constitutional isomers. Okay, so what's the relationship between those two? Well, is there a axis of rotation between those two? Before, after. So no axis of rotation because they're clearly different. If we go and look at it from this perspective right here, is there a plane of symmetry this way? Yes, but that's not the plane of symmetry we need because we are chopping those two protons in half. So yes, there's a plane of symmetry, but that's not what we're looking for. We need to draw a plane of symmetry that cuts or puts those two hydrogens on either half of the plane. And so if I draw it this way, the two hydrogens are on either half, but look down below. Hydrogens on this side and methyl groups on this side. So there's no plane of symmetry. So it doesn't matter how you rotate it or look at it, you will not find a plane of symmetry. So those two protons are not equivalent to one another. So that would be C and that would be D. Because you can't find a plane of symmetry with those two protons are diastereotopic to one another. So in this molecule here, you would expect 4 signals. So these are homotopic, no wait, what? Enantiotopic, diastereotopic. Okay, what if we take and look at Put a chlorine right there. How many signals would you expect for this molecule? We'll take a moment and draw in all your hydrogens and make sure you're drawing in the stereochemistry. That is critical. Because if this is what you do, like this, and just draw in lines, you won't be able to find planes of symmetry. Because everything's in the freaking same plane. Those are tetrahedral carbons right there. It doesn't look that way. But if your test problems or practice problems, examples in the book, draw it like that, then you have to adjust it and draw in the stereochemistry. And then oftentimes people forget, hey, there's a hydrogen hanging out right there. All right? So if we do this without a model and do it quicker now, what's the relationship between those two protons? Plane of symmetry. There's no axis of rotation. So those are equivalent because they're enantiotopic. If those are equivalent, then those would also be equivalent to one another. All right, BB. So the B protons are enantiotopic, giving us one signal. But why is HA and HB, why are those not equivalent to one another? Well, if you take this and make a model, you're not going to see an axis of rotation, and you are not going to see a plane of symmetry. So what's the relationship between these two? They're diastereotopic. And then this hydrogen is just all by its lonesome right here, so that would give us another signal right there. So this molecule here would give you 3 signals. Let's see here. I'm on a triangle kick, so let's do another one. What if I did a dashed methyl and then a wedged methyl? And so we're going to have a hydrogen there and then a hydrogen there. I didn't draw that very nicely, did I? And then we would have our hydrogens here that we need to pay attention to, right there. Whoops. I dropped the marker, and now I can't seem to find it. So for this one, let's take a look at the methyls. What's the relationship between those? What do you think? Those are homotopic, and they are equivalent. Why is that? Because we have an axis of rotation. You would not be able to tell the difference between before you rotated and after. And so the same thing for those. Axis of rotation, making those homotopic. And same for those. Axis of rotation makes them homotopic. So each set are homotopic to one another, but there are 3 chemically distinct groups of hydrogens to give us 3 signals for that one. Let's see here. Let's do this one. Then we have our methyls coming off like that. CH3, CH3. We have protons here, protons there. So the two methyls, you will see that there is a axis of rotation right here, making those guys homotopic and equivalent. A and A, those are homotopic to one another. If I ask what's the relationship between this wedge hydrogen and that wedge hydrogen, you will once again see that there is a axis of rotation. You won't know the difference before and after, so that's going to make those guys homotopic and equivalent. Now what's the relationship between these two right here? Okay. When you take a look at those two, you will see that there's also an axis of rotation. Let's see, let's take a look at that. Hang on, about the relationships between those two. Let's take a moment and let me think about that a little bit longer. So when we ask the question, what's the relationship between this proton and that proton, you will find that they're enantiotopic and equivalent. So these four hydrogens right here are all equivalent to one another. Now, what about these two protons here? Well, is there an axis of rotation? Yes, there is, for those two as well. So those are equivalent to one another, and those would be homotopic to one another. All right. Let's see, let's do two more for this video here. And then we will call it a day. How many signals would we expect for this guy right here? So we have to understand that this is a methyl, so those are just all equivalent. That's just going to be A. We see that this right here is also a methyl, and those three protons have to be equivalent. But is this methyl and that methyl going to be equivalent to one another? Clearly no. That methyl's attached to an oxygen. That methyl's attached to a carbonyl. Different connectivity. So it's going to be different. So we'll call those protons B. But now we have to be careful. Hybridization state here, we have a H. Wait. Oh, I guess we'll do it like that. So what's the relationship between these two right here? Is there an axis of rotation? No. There's not, but is there a plane of symmetry? And the way that you're going to be able to see this plane of symmetry is to take this molecule that's in the plane, okay, and then rotate it 90 degrees. And then when you rotate it 90 degrees, look down the backbone of that molecule, and you'll see that there's going to be an equal half. There's going to be a plane right down the middle, making those guys enantiotopic and equivalent to one another. So we would expect three signals for that molecule there. Now, I lied. Let's do two more. What if we had something like this? 1, 2, like that. Okay? So we have methyl there. Now we have these methylenes right here. So this methyl is attached to carbonyl, that methyl is not. So those have to be chemically distinct. A, B. These two protons, what's the relationship between those two? you're going to see that they are enantiotopic. So they're equivalent. If you take that whole molecule, rotate it 90 degrees, and look down it, you're going to see that there's a plane of symmetry. What's the relationship between these two? The same thing. Plane of symmetry, those two are enantiotopic. They're going to be equivalent. But HD and HC, why are those not the same? Because if you did the replacement test, you'll see that they're going to be constitutional isomers, and you won't find a plane of symmetry amongst C and D. Doesn't matter how you rotate these bonds or try to find planes, it's just not going to work. So in this particular one, we are going to have A through D, so 4 signals. Okay? But what if I change it up ever so slightly? Take a look at this. What if I change it up by doing something interesting? What if I just say I put an alcohol right there? And that's the molecule signals. Well, you guys are smart people. You realize that we have 3 bonds all in the same plane. That's not possible. So this has to be a stereocenter. Do I know if it's an R or an S? No, I do not. But I know it is a stereocenter. So I'm just going to pick one. I'm just going to say we'll put the wedge on the OH. If it just shows stick bonds right there, then you have to just pick one. And then we know that we have a proton there. Okay? And then we have our protons there. So if we start off easy, we know this is going to be a signal, and that's going to be a signal, and those two cannot be equivalent because they're in different chemical environments. We know that one proton is going to give a signal. We know this proton on the alcohol is going to give a signal, so we have 4 already. And so what's the relationship between these 2 protons right here? Well, we have to be very careful because what do we have here? We now have a stereocenter, that messes up the symmetry argument. If you take this molecule and rotate it 90 degrees and take a look down, and we're asking the question, are these equivalent? You will see both hydrogens on either side of the plane. But as you look further and further down the molecule, you'll see that, hey, we have a hydrogen on one side and an OH on the other. And so there's no plane of symmetry when you look down the molecule. So since there's no plane of symmetry between these two, those make those diastereotopic. And so since they're diastereotopic, they have to give separate and distinct signals because they're not equivalent. So E and F. So how many signals is this simple molecule going to give? 1, 2, 3, 4, 5, 6. 6 signals. So it's very, very important that you understand symmetry arguments and the replacement test, and not creating these shortcuts that many people make that are false. And one of those shortcuts that people make is saying, oh, methylenes are always going to be equivalent to one another. It happened here, happened there, happened there. Did not happen there. So you can't make this shortcut up in your head. You have to see the symmetry of the whole molecule and do replacement tests to really make sure. So I think that's where I will end this video.